problem from section 4.2, weight and drag force. This is problem number 51 on page 114. This problem in particular deals with weight as opposed to drag. So this is more of a problem about weight. Before watching this video, I encourage you to attempt to solve the problem on your own and compare the answers you get to the answer key that's on Blackboard, and then approach this video if you still need extra assistance. Our problem is this. We have a helicopter. Here's my helicopter. It has a winch, or a cable with a winch, which is like a winch is a cable attached to a hook at the end of it, and all of that is attached at the other end, opposed to the hook, is attached to a motor that rotates and can pull in or spool up the cable at the end of it, having that hook. That's what a winch is. All right, so we have a winch that's 12 meters long going down to two people that are hanging from the end of that winch. The mass of those two people together combined, so the mass of our system down here, represented by this box, is 120 kilograms. The maximum force that this winch can apply to any load is 2,000 newtons. And that will apply to our part A. For our part B, we'll know that the force of pulling on these two people that are being rescued is a force of 1,200 newtons. And then for part C, we're asked to find out how long it takes the helicopter to pull our two rescue victims, given that we have 12 meters worth of cable that needs to be pulled in. Part A, we're asked, given a capacity of 2,000 newtons of force that the cable can supply, what is the maximum mass it can lift? All right, so if we looked at a free body diagram in this case, we would have some force pulling upwards. As we'll see in section 4.3, that would be a tension force. And then we have some force going downwards that's acting on our system here. All right, this is a free body diagram of our two rescue folks, that system that's represented down here. We have the weight. Now in this case, if they're just being suspended or lifted, and say lifted at a constant velocity, then if we were to look at the sum of the forces that are acting on this object, we have the tension force, or the force that the cable is applying to those two rescue folks, and the force of gravity on our two rescue folks, and that would be what we call weight. That's, as always, equal to the mass times the acceleration. If we have constant velocity, then this is equal to 0. Right? Assuming we have a constant velocity, or they're just hanging there. Now, if we turn these into magnitudes, right, we know that the magnitude of the tension force, or the force that the cable exerts on the people, is in the positive direction, whereas the weight force is in the negative direction, so we'll say negative. What this leads us to conclude is that the tension and the weight force must be equal, because the difference between the two is equal to 0. So the two must be equal to each other. All right. Do we know the magnitude of either of these forces? Well, the force we're asked to find really here is the tension, or the force of the cable on the people. We know that if it has a tension force of 2,000 newtons, right, if that's the maximum force that it can apply, what we're asked to find is what maximum mass it can lift. Here's how we would represent the weight of whatever it's lifting. So in this case, in part A, we're neglecting this 120 kilogram mass because we're talking about this m being the maximum mass that it could carry, given that it breaks after 2,000 newtons of force. Well, we don't know the mass, that's what we're trying to find, but we do know that the gravitational field on planet Earth, which we assume our helicopter is on, is 9.8 newtons per kilogram. right? This mass is measured in kilograms. More simply put, we would just say m times 9.8 newtons equals 2,000 newtons. Or really, would you say 9.8 for greater simplicity. So we have 2,000 divided by 9.8. That should give us the maximum mass that this cable can lift, and that is 2,000 divided by 9.8, our gravitational field. Here we only have one significant figure in the 2,000, so our mass is just 200 kilograms. That's our answer to part A. That's the maximum mass that our cable can support. Now for part B, 200 kilograms, our maximum mass that our cable can support. Now for part B, we're asked if it were to apply a force of 1,200 newtons, what is the rescuer and victim's acceleration? We'll draw a free body diagram again. So here, if our force upwards, our tension force, is pulling up, that's the cable, and then we have the weight down. We do our sum of the forces again. It's a very similar operation that we did above. We have the tension and we have the weight. This is now equal to some non-zero acceleration, we assume. Okay. We'll turn these into vectors, or rather into mathematical quantities. We have the tension pulling up, we have the weight pulling down, and then this gives us the magnitude of our acceleration. Well, we know the tension force. It's provided in the problem as 1,200 newtons upwards. Okay. The magnitude of the weight force, or the force due to gravity on our objects, is whatever its mass is times gravity at that point in space. Okay. We can fill in what our mass is because it's 120 kilograms. Right? We go back to our problem. 120 kilograms is the mass of our rescuer and the victim. 120 kilograms times a gravitational field of 9.80 newtons for every 1 kilogram. This gives us equals our mass times our acceleration, which again we know this mass represents the mass of our object that is undergoing these forces, right? And now we can solve for our acceleration. I'm going to simplify this left side first of all. So I'm going to do 120 times 9.8 newtons per kilogram. That gives me 1,176 newtons. Simplifying this left side even further, so the 1,200 newtons, that's the force of pulling up, minus the force due to gravity or the weight, gives us a net force of 24 newtons on our object, with a mass of 120 kilograms. F equals m times a, so our acceleration is 24 divided by 120, or 0.2 meters per second squared in the positive direction. Because the net force is in the positive direction. All right, now for part C. All right, for part C, we're saying, given that our average acceleration is in the positive direction at 0.2, I think is what we said. Yeah, positive 0.2 is our average acceleration, meters per second squared. Given that we're moving from rest, so our initial velocity is 0 meters per second. And the distance from the rescuer and the victim all the way to the helicopter was given in the problem by 12 meters. So that's the displacement. It needs to move positive 12 meters, or 12 meters in the positive direction. We're asked to find the amount of time that this movement would take. So I need an equation that relates time, distance, initial velocity, and acceleration. There is one that I can think of, and that is our second kinematics equation. Here's our second kinematics equation. What's going to be tricky about this is we're going to have a quadratic. We're going to have to solve a quadratic equation. If we fill in all of our numbers here, we have positive 12 meters equals our initial velocity of 0. So the quadratic will fall away. So this term, because we have no initial velocity, it'll just be 1/2 positive 0.2 meters per second squared, and then times our time squared. So we need to get time by himself. So we multiply each side by 2 and divide by 0.2. So 2 times positive 12 meters, and then divided by 0.2 meters per second. That's a positive. That gives us time squared. And now we need to take the square root of both sides, and that'll give us just t. So I put this in my calculator as 24 divided by 0.2, which is 120. Square root of 120 is 10.95 seconds. I have two significant figures here that I'm working with, so our time is 11 seconds. So recapping, the maximum mass that our cable that has a pulling force maximum of 2,000 newtons, it can support a mass of 200 kilograms. Applying it directly to our problem of the 120 kilogram rescuer and victim, if the cable applies a force of 1,200 newtons that counteracts the force due to the weight, which was 1,176 newtons, the acceleration of the rescuer and of the victim would be positive 0.2 meters per second squared, or 0.2 meters per second upwards. And then finally, given these kinematics variables that we have, we know that it would take 11 seconds for the winch to pull those two personnel into the helicopter, given that force which produces this acceleration, and that they were being pulled from rest, and that they had to travel 12 meters up to the helicopter. All right, thank you.